So good afternoon, all. I welcome you once again in the second lecture on satellite navigation. So, in the last two lecture and the demonstration part, we have seen that the satellite navigation provides us the latitude, longitude, and height of a place. It is a type of a surveying equipment. It do not require a clear line of sight requirement. So, like this, we have covered some of the features of the global navigation satellite system, like the accuracies, standalone accuracies of the GNSS. We also saw that four global navigation satellite systems are operational right now. That is the Navistar GPS from the US, GLONASS from Russia, Galileo from European Union, and BEDO from China. Out of these, GPS, GLONASS, and BEDO, they are fully operational, and Galileo is also nearing its completion. Thereafter, we were discussing about the different segments of the GPS. So, the entire satellite navigation can be basically divided into three components or three segments. One will be called space segment, that will consist or comprise of the satellites in the space which are orbiting in their respective orbits. Then there are control segments on the ground to monitor the satellites and do the routine services like uploading or updation of the signals through the two-way communication with the satellites. So we can do the health monitoring of the satellites with these control stations along with the updations. And then the third segment is the user segment. So we basically fall in the user segment, wherein we are using the GNSS receivers for our required applications. The prime space segment contractors over the time has been Rockwell International in the beginning. Thereafter, the tenders has gone to the Boeing, Lockheed Martin, and again then Boeing. And currently, the Block 3 is with the Lockheed Martin. So, Block 3 is the responsibility of the Lockheed Martin for the fabrication of the GPS satellites. Now, these all computations are happening in the World Geodetic System 84, WGS84 system. That is the coordinate reference which is being used in the satellite navigation. There are other systems also like parametrism, which we have discussed on Monday by different countries like the Russia, Russia, European Union, and the China. They also have their own datums. However, the transformation parameters are known, so they are interconvertible, and that is how we can use all of them together in a single mathematical solution, and all will be done with the help of the software. So a general user need not to worry about that actually. The headquarter is at the Colorado Springs at the US Air Force Space Command station. Then we have seen that the different generation or the blocks of a space segment has been there, which I explained in the lecture on Monday. And we have seen that the current block which is on launch is the block 3, for which 6 satellites are already operational, as you will see in the next slide. The operational satellites can be seen at the gps.gov website. All the datasets and the information are freely available there, and we can see that these are frequently updated also as the changes are happening. So in this particular slide we can see that in the snapshot that block 2A has 1 operational, block 2R has 11 operational. So we will see that over time they have updated it, and earlier we had 10 operational in block 2R, and block 2A all became obsolete by completing their life, and then the block 2R has become 8 recently, and currently we have 6 operational block 2R satellites, as you can see here, and 7 are operational in the block 2RM, and 12 are operational currently in block 2F, and in block 3 uh, 6 satellites are operational. So this screenshot I have taken on day before yesterday, that is Monday. So we can see here that we have 31 satellites fully operational in the Navistar GPS constellation, and the block 3 has L1, L2, L5, all the 3 carrier wavelengths are there, and these are intercompatible with the Galileo and the QZSS and the BDO systems. So some of the wavelengths, particularly like the L5 wavelength is there, L1C is there. So these are compatible between the systems for the interoperability purpose. Now, the main responsibility, as I was telling, it was with the Lockheed Martin and the Boeing. So they have a very long experience of doing this job from 1980s or so. Okay, although first satellite was launched in 1978, so we can say 70s basically. So from 70s onward, these agencies has been preparing the satellites for the launch and maintenance of the constellation of the Navistar GPS system. So the main difference between GPS and GLONASS is that in GLONASS each satellite has its own frequency. Like in case of GPS, what we have seen that all the satellites have the L1 and L2 carrier waves. From block 2 of onwards, we have L5 also. But from the beginning, GLONASS is designed in a bit different way, that its satellites on the geopodal position, antipodal positions basically. In antipodal positions means geographically which are on the two sides of the earth. So they are having same frequency. So basically if they are maintaining 24 satellites, so 12 satellites have one set of frequencies and another 12 satellites will have duplicate of that, you can say. But they will not intervene with each other because they are placed opposite to each other. So they will not be seen by a single receiver at any point of time. So we have 12 set of frequencies that way, which are used in the GLONASS. And if the satellites are more than 24, then we will have the 13th, 14th category also. As here we can see during this screenshot what we have taken, 27 satellites has been operational. So 27 satellites means, so we will have a set of 14 different frequencies which are explained here. I will just show you how they are made actually. Maybe it is coming in the slide. Okay. So these satellites are also working with the cesium and rubidium clocks, and hydrogen measure clocks are there, which are able to provide accuracy of picosecond or better. So they are 1 in 10 to the power 12, 1 in 10 to the power 13, 1 in 10 to the power 14. That kind of accuracies are being provided by these clocks, because here timing is a very important factor, because we are using trilateration method wherein we are computing the distance between the satellite and the receiver. So that need to be computed in a very accurate way. So here the GLONASS also has a analogous way. There we were talking about block 1, block 2, block 2R, block 2RM, block 2F, block 3. In case of GPS, in case of GLONASS, they have different generations which have different names. So here it is the GLONASS, GLONASS M, GLONASS K and GLONASS K2. So currently the GLONASS K2 series is going on, and we can see here also, like the GPS, there is an improvement in the technology in terms of efficient systems, less power consumption is required, and less weight is there for the satellites. So we can see that initially the GLONASS was also having a life span of 3.5 years, then it became 7, and then now it is 10 years or possibly better than 10 they are able to get. So in case of GPS, it's a 6 orbit based design. The orbits are at an inclination of 55 degree to the equator. all the satellites are placed in such a way that they are available or visible from minimum 2 ground stations. The design has been made like that. So 6 orbits, 4 satellites in each, that means 24 satellites are there minimum. As we have seen in the previous satellite, 31 are active now. So that means we are maintaining a lot of redundancy in the Navistar GPS satellites because we have large number of applications based on that. So at any cost, we do not want to have a crisis that we have less than the minimum number of required satellites. So a lot of redundancy is being maintained, and this is managed by the US National Space Based Positioning, Navigation and Timing Executive Committee, that is the PNT Executive Committee. So they take the different decisions regarding this. The GPS satellites are placed in 12 hourly orbits, and from any station, from the time of visibility to time of setting of that satellite, when it moves out of the range, 4 to 5 hours visibility is there for a particular satellite from a ground station. So as per the basic design, 5 ground stations has been made, one at the Colorado Springs, Hawaiian Islands, Ascension Islands, Diego Garcia and the Kwajalein Islands. So these are, you can see they are quite well placed geographically to cover the entire space, and this is the basic design. So these 5 stations has to work properly. However, with the time and the improved scenario in today's condition, where a lot of collaboration is going on between different countries, different space agencies, now there are large number of stations at different places like uh, Argentina, Bahrain, United Kingdom, Ecuador, Washington DC, Australia, and so on. So currently there are 16 monitoring sites which are available. So that means from initial 5, now we have gone to a number of 16. Out of this 16, 10 are maintained by the National Geospatial Intelligence Agency of the USA, and the 6 are maintained by the USA Air Force. So like that, this distribution is there now, which is over and above the minimum requirement of those 5 stations, which are part of the basic planning, that all the satellites are visible minimum from the 2 ground stations. But in the this current design, you can see that the satellite will be visible in more number of ground stations now, because of the more dense distribution of the ground stations. This will help basically in the improvement in the values, because all the parameters which are corrected, like the ephemeris data, satellite clock data, in the modeling purpose, for the orbital tracking, various parameters for the orbital dynamics, we will have lot of redundant data sets because of the large number of ground stations. So these data sets are collected from the 5 monitoring stations by the master control stations, whose responsibility is to improve or correct these data sets. That means removal of the errors from them, and that will include the mathematics for the error distribution also. So with the increased redundancy in the observations, the error distribution can also be done in a better way, improving the accuracy of the overall measurements. So as I was telling in the earlier case, yesterday's discussion of the query session, it takes about 10 days to 2 weeks time to do the corrections by the master control station for the preparation of precise ephemeris data from the broadcast ephemeris data. Broadcast ephemeris data is the data which the receiver is receiving as soon as it starts operating. So the live data which is being detected or recorded by the receiver, that is the broadcast ephemeris data, whereas after corrections it is called the precise ephemeris data. So for important tasks like the national network, precise ephemeris data are utilized. So that means it takes time for the post processing time to produce the desired results for national networks. For urgent requirements, of course, we can depend on the some broadcast ephemeris data or predicted data sets are also available from the site, so those can also be utilized. For the Russian region also, a similar set of ground stations is distributed. So here we can see, because of the better geographical condition of the US, they have a widespread network across the globe. However, Russia also has a very huge area, and because of that they are also able to maintain a large number of stations which are distributed globally. uh, However, the as we have seen, the US has a bit more upper hand in this case because of their more influence geographically. So as we were talking about that, the GLONASS use the antipodal satellites which are geographically placed opposite on the side of the Earth. They carry the same frequencies. So here they are carrying the L1 and L2 frequencies, but this L1 and L2 are provided for different set of satellites using this formula. So it is 1602 megahertz plus 0.5625 megahertz. Okay, so that will be one set of that. For another it will be, the n will be 2, for third set it will be 3. So like that, L1 will have multiple wavelengths. Okay, so that is how we have 12 or more number of L1 frequencies and 12 or more number of L2 frequencies which are used in GLONASS, and they are designed in such a way that the f2 by f1 ratio is kept at 7 by 9. So that is how the design has been done. The cesium atomic frequency for the GLONASS, they are operating at 5 megahertz, and they are also providing the position, velocity, and timing primarily, along with some other parameters like the acceleration vectors at every epoch. So we talked about the satellites in their orbits, so that form the space segment. Then we talked about the ground segment stations which are distributed all over the globe. We have seen it for the GLONASS and the GPS. Now third one is the user segment. So user segment is, as I already discussed, a large number of users are there globally now, and almost every one of us is benefiting the certain applications by each of us with the GPS, knowingly or unknowingly. Okay, because whatever facilities we are using, so they are, many of them are already using the GPS. So maybe in many of the applications, like if you are taking a flight and you are going from one place to another place, you may not be directly using the GPS, but the pilot may be using for the flight purpose. So indirectly we are getting benefit from the GPS. Now why we are using GPS? The main advantage, as we discussed, is that it works on a common coordinate system. So for all international applications, global applications, this provide us a country independent coordinate system. Otherwise all the countries, their survey departments, they have prepared some local best fit curves and the coordinate system. However, this provides a common coordinate system for the global scale, so it is very much usable by all. It is very weather independent, so we need not to worry about the weather conditions. In all type of weather conditions, we will be getting the GPS signals which are free of line of sight requirement. They will be providing us high geodetic accuracy. That means it will take care of the three-dimensional shape of the earth, and corrections are carried out for them, and the GPS will provide us the coordinates day or night, and it can be used for wide range of applications, and definitely it has a economical advantage. So like that, we see that there are large number of benefits which are there from the GPS. So that's why we are using the global navigation satellite systems in general for various surveying requirements, or various other apps where it provides convenience in building those apps, as they can directly get the input of the location from the GPS. So primarily, after the so long discussion, we have to understand that the GPS provides us location, okay, in a common reference frame all over the globe. So it provides us location with respect to the WG34 datum. So we get the latitude, longitude, and the height. And we discuss the three segments: satellite, ground segment, and the user segment. Now we will see that how the GPS works. So basically, GPS works in a one-way ranging principle. Okay, so the signals are only received by the receiver. No signals are emanated back from the receiver. So in this GPS, what is happening that the location of the satellites in the respective orbits are very precisely known, and these reference stations which are there in the form of GPS are utilized to compute the position of the receiver on the ground. Okay, so known is in the space in this case, unknown is on the ground. Okay, that was the problem which was formulated by Frank McLaury, and it has been seen that it is possible to do so, resulting in the development of the transit regional system. We talked this on Monday, and later it graduated to the full-fledged global system, that is the Navistar GPS. So the signal which is coming from the satellite to the receiver is time tagged. So at time t1 it starts from the receiver, and at time t2 it reaches the receiver. So t2 minus t1, that is the delta t, is the time of travel of the signal. So this delta t, when we multiply with the velocity of light, what we will get? We will get the pseudo range, that is the distance between the receiver and the satellite. Now we call it a pseudo range because in the surveying subject, distance is referred as range. We have added a pseudo to the range, so it is pseudo. So pseudo means false. So we are using a term pseudo range because we know that there are certain errors in the computation of the range, and these errors need to be corrected. So like this, we compute the pseudo ranges from one satellite position which is known. So the position of the satellite is known. However, it is a measurement of distance, so it is a scalar quantity. So that means if we create a sphere using that pseudo range, it will result in a sphere. And now the receiver is somewhere on the sphere, so it is quite a large uncertainty in the measurement. So what to do? So in that case, what we will do, if we have two known position of the satellites and we have computed two pseudo ranges, C delta T1 for one and C delta T2 for the second satellite and C delta 3 for the third satellite. So what will happen? We see that when we are intersecting two spheres, then it results in a circle path which result after the intersection. So from the whole sphere where there is a possibility of receiver, we are able to bring it down to uncertainty over a circular path. And when we intersect three spheres using the pseudo ranges, it results in the 2 points where the three spheres intersect each other, and these 2 points possibly represent the position of the receiver. So one is the real solution, another is the vague solution. Okay, so that is how we are able to compute the position of the satellite. Here this is another figure which is very much available in the literature, but in this case we have assumed that the earth is on this side. Okay, so that is a bit unfair way of assuming, so I prefer to use this one. This you can see in the free ebook GPS, the first GNSS, which I have referred to you to go through on the first day, that is on the Monday. We were talking about the time here, and I was repeatedly telling that time is very important, because as we see here, if we have a error in 1 microsecond, that microsecond error will result in an error of 300 meter. If we have a nanosecond error also in the computation, what will happen? The distance between the satellite, which is acting as a orbiting control station, and the receiver on the ground, the range will have a error of 300 meter in case of 1 microsecond error. In case of 1 nanosecond, also there will be error of 0.3 meter, that is 30 centimeter. So many of the applications, they will not be in position to tolerate these kind of errors, like water resource applications. So there the pressure head is very important, so the height is very important. When we are going for engineering construction, that time also we cannot tolerate. So that is why we are looking for a picosecond or better accuracy in the measurement of the timing. So now what is happening, that we are having unknowns latitude, longitude and height, and we have a fourth unknown called clock bias, which is resulting from the synchronization problem between the atomic clock on the satellite, either the rubidium cesium clock or hydrogen measure clocks, and the quartz clock on the receiver, which is a relatively a cheaper clock which we are using in the receivers. So that sync problem results in a unknown called B, which is referred as the clock bias. So now instead of 3, actually we require 4 signals. So we have seen this figure geometrically, where how we are using the 3. So that is a geometrical description for basically performing the trilateration. Okay, so that is a type of triangulation which we are trying to perform here, to zero down to a position of the receiver, or computing the position of the receiver. So these type of equations we form, so where P1 is the pseudo range for the satellite 1, which we can compute by C delta T1. Okay, P2 is the pseudo range for the second satellite. The coordinates for the first satellite are x1, y1, z1. For the second satellite, x2, y2, z2. For third, x3, y3, z3. And fourth satellite, x4, y4, z4. These coordinates are embedded in the signal which is received by the receiver from the satellite, along with the timing also. And that timing we are using for computation of P1, P2, P3, P4. So in this equation, we see that the xi, yi, zi, that is the position of the ith satellite vehicle, that is known to us. P1, P2, P3, P4 are also known. So what is unknown in these 4 equations? Unknowns are x, y, z and b. So these are the 4 unknowns which represent the position of the receiver on the ground and the clock bias. So using these 4 unknowns, we will compute the position of the receiver. So it is a non-linear equation set, and thus it can be solved using computers for a quicker result. Manually it will take more time. However, the systems are very efficient and they will provide a solution in the real time. So we have discussed few things, so we can have possibly 2 minutes of quiz time. You can go through the questions here. A similar pattern of exam will be there later for you. So you just I will take a break of 2 minutes, and you use this time for going through these questions. Then we will discuss again. Okay, so I hope you have seen the questions, and we have been discussing them in the recent slides also. We'll continue further. Now we'll come to the GPS time, which is computed a bit differently from the time we are using in our day-to-day routine, that is the International Atomic Time, or the UTC time, which is also called the Zulu time. So this UTC time basically starts from January 1, 1972, and it is referred as the Global Civilian Time, which we are using in our day-to-day life. However, the GPS time has a different date of start, and it is computed from the night 12 o'clock on 6th January 1980. So that was the first Sunday in 1980, and based on that, there was a difference of about 13 leap seconds at the beginning between the International Atomic Time and the GPS time. Now, timing in itself is a big science actually, and this difference between the GPS time and the UTC or the International Atomic Time is not a constant. It is a variable basically. So, because of the nutation precision, different movements of the Earth, change in the rotation also, all these things make a difference in the timing. However, we need not to worry as a general user of it, and that will be taken care by the respective agencies and incorporated in the computation of the GPS time. Okay, so that the final accuracies will be better than picosecond. Okay, so they are better than 1 part in 10 to the power 12 in any case. So usually 1 part in 10 to the power 13 or 1 in part in 10 to the power 14, that kind of accuracies are maintained. And there is a repetition of the time here. So effectively GPS time starts with 0 at the beginning of each week. So there is a different way of addressing the GPS time, which gets reset in every week. Next thing is the GPS signal structure. Okay, so I'm just revising a bit from the previous discussion. So we have seen that the GPS provides us the PNT, so position in terms of lat long height, then velocity, and then the timing. So these are the basic parameters which we are getting. Then we discussed about the different generation of satellites blocks. Thereafter we discussed the different segments, and after that we discussed the 5 steps, easy steps to work to compute the location of the receiver. So we have seen the equations used for the computation of the location using the pseudo ranges and the nonlinear solution. Now after that we are coming to the GPS signal structure. So basically here also we can see that we have 2 carrier waves, L1 and L2, which are high energy waves, and over them we have some codes. That is, the CA code is the course acquisition code, P code is the precise code, and P code is basically encrypted using a W key, and thereafter it is called the Y code. And P code has a frequency of 10.23 megahertz, which is referred as the fundamental frequency. In case of GLONASS, it is considered as 5 megahertz. In case of GPS, it is 10.23 megahertz. Now the CA code is available on L1 carrier wave only, whereas the P code is available on the L1 as well as L2. Now CA code and P code are less energy electromagnetic radiations. You can say these codes are having less power. However, they are modulated on L1 and L2 so that they can reach from the satellite to the receiver. Besides this L1, L2 carrier waves and the CA code, P code, there is a 50 bit per second satellite message also, which consists of the ephemeris data, that is the instantaneous position of the satellites in the orbits, and the almanac. Almanac is the chart of the satellites, GPS satellites, which takes around 12.5 minutes for the download in a GPS receiver. So one satellite data, it takes about 30 seconds for the purpose of almanac. So for around 25 satellites, we can say 12.5 minutes, or 30 satellites are there. So in that case, it will take about 15 minutes. So when we go for the differential GPS surveys, then we normally operate them even if the baselines are short, something like 20 minutes to 30 minutes or 40 minutes, that kind of observation we take. So in that time, almanac chart also gets downloaded The wavelength of the L1 wave is 19 centimeter, L2 wave is 23 centimeter. So basically what happens that initially we used to have code based solutions. So code based solutions provides us accuracy of the 70 to 100 meter in the initial days before the 1st May 2000, when selective availability was an operational phenomena, whereas the US agencies deteriorate the signal intentionally. But from 1st May 2000 they have stopped that, and thereafter we started getting 10 to 20 meter solution. So for the CA code solutions, even if we do the differential survey, our accuracy will be of the order of a meter or so. Okay. So in the latter part, what has happened that it is found that even the carrier waves, which were initially mandated to carry the codes only and not for the computation of the location of the receiver, it is found that the carrier waves L1 and L2, they can also be utilized for the computation of the location of the receiver. So that gave rise to new method of solutions, which we refer as the phase based solutions. So one set of solution is the code solutions, another set of solution is the phase based solution. Now here what has happened that the P code wavelength is of the order of 29.3 meters. The wavelength of CA code is about 300 meters, whereas the wavelength of L1 is 19 centimeter, wavelength of L2 is 23 centimeter, and wavelength of L5 is about 23.5 centimeter, 25.5 centimeters. Okay, 23 centimeters for the L2. So when we are computing the phase, the electronics has the capability to measure the phase within an accuracy of 1%. So that means if the wavelength is 19 centimeter, we can compute the phase which is equivalent to 19 centimeter with an accuracy of 1%. Now 1% of 19 centimeter is how much? 0.19 centimeter, that is 1.9 millimeter. And for L2 it is how much? 1%? 0.23 centimeter, that is 2.3 millimeter. So that is how what happened. Our computations which were running in the order of meters, they suddenly came with higher accuracies of the order of centimeters or millimeters when we developed methods using the phase. So phase solutions provide us better accuracy, and that is basically one feature available in the costly receivers which provide us phase based solutions. Our usual receivers, handheld receivers, which are providing us relatively less accuracies of the order of 10-20 meters or so, they are basically working on the code based solutions also only, and that is also coming on the L1 wavelength. Whereas in case of the phase based solutions, we are able to get L1 and L2 advantage both actually. Okay. For the military receivers which use P code, the P code is available on L1 and L2. So thereby what happens that the ionospheric errors, they can be computed using the P code by the authorized or the military receivers. So the P code receivers provide higher accuracy than the CA code based receivers. For the authorized receivers or the military receivers also, to catch hold of the P code, basically they need CA code actually. So first the CA code is being retrieved by the or connected by the receiver, and that helps in getting hold of the P code. So that is the way the military receivers also function. So it's not that in military receivers CA code is not required. CA code is required there also. Okay. Now this was the basic configuration. Thereafter L5 has been added from the block to F, and it also provides I5 and Q5 codes for the safety of life applications. it is having more anti-jamming properties, and it is L5 is available on the block 2F satellites, and L2C signal has been added thereafter. L1C signal is also added along with the AM code. So this is the current configuration for the signals which are currently working on the GPS. However, the L1C and L2C, they are still in the pre-operational testing phase. We can see here L2 is available on 24 satellites or more since 2007, but it is still in the pre-operational testing phase. Now, besides this L1, L2 and L5, there are two other wavelengths, L3 and L4, which are used by the US defense for the detection of the atomic flash anywhere on the globe. So it is called a nugget system. So for the purpose of the nuclear detection, any activity of that nature is happening. So in that also, the GPS receivers helps for the detection. So L2C signals begin from GPS block 2RM in September 2005, and these are designed to meet the commercial needs. These are civil moderate codes with a time period of 20 millisecond, and then there is a civil long length code also, which has a time period of 1500 milliseconds. So these are available, but we are currently not using them, but a time will come when we will be able to use it. So what difference it is going to make is that it will make us possible to get the ionospheric correction in the civilian receivers also. Okay, as we see in the previous slide, the similar thing is carried for the P code enabled receivers here, because P code is available on L1 and L2 two wavelengths. So once L1C, L2C, these civilian codes are available on two different wavelengths, the civilian receivers will also be able to get higher accuracy. L5, as already discussed, it started from the block 2F, and L1C is starting from the block 3. So the first launch was done on 23rd December 2018. So block 3 is actually going to replace all the earlier blocks in the times to come, and for that a major rehauling exercise is going on, because for block 3 we have to replace all the hardware on the ground control segment also. Not only the satellites are new with the new technologies, but the ground segment in terms of hardware is new, and the software which is used is also new. So as in the previous lecture I told, about $6 billion expenditure is being incurred in the establishment of a new network which will be full of block 3, and which will provide a more cyber security based GNSS system. Now P code is a very long code, and it's complex, and it takes about 260 plus days, 266 days for getting completion. So it is a binary code 0101 kind of a code, and it's a very long code. Time period is 266 days, in contrast to the C code, which is a very small code with a time period of 1 millisecond. So that is the contrast in the two type of codes. CA code is having a time period of 1 millisecond. Okay, it is also called the gold code. For the GPS it is 1023 bit long. For the GNSS it is 500 bit. So red is used for the GLONASS here, and black is referring to the values of the GPS. Similarly, sequence length and the chipping rate is also different for the GPS and the GLONASS, and this is providing the standard positioning service to the civilian users. Whereas 5.11 megahertz is used by the GLONASS, and 10.23 megahertz is used by the P code. Okay, so that is how the two codes are used, P code and the C code, which are quite different with respect to each other in terms of the length of the code, in terms of the time period of the code, and P code is encrypted also. After encryption it is called Y code, it is called anti-spoofing, so AS. So let us remember, in the GPS we are talking of two terms. One is the SA, that is the selective availability, which is a type of intentional degradation of the signal, and anti-spoofing is AS, which is basically referring to the encryption of the P code into a Y code. So the navigation message is also coming up with the signal which we are getting, and it helps us in solving the user position equations. It is a 50 Hertz signal modulated on the L1 and L2. It helps us in computation of the pseudo Keplerian orbital elements. It is determined by the control center via the ground tracking stations. So 5 stations were planned in the beginning, and now we have 16 stations. This navigation message basically implements the orbit to position algorithms. So how the orbital ephemeris data is used for the location computation for the satellite in the orbit, and thereafter we are computing the coordinates of the receiver using the pseudo ranges and doing the trilateration exercise by building the different spheres and intersection of those spheres. Now these wavelengths which we are talking about so far, like L1, L2, L5, for local issues within a country, like we are starting a FM radio or some other kind of transmission, we decide at the country level. Our telecom industry government department will do that. However, for the global applications, International Telecommunication Union takes those decisions, and they allot different frequencies to different agencies. So for GPS they have allotted L1, L2, and they allotted L5 later. In case of IRNSS, Indian Regional Navigation Satellite System, what happened that ITU allotted us with the L5 and S band. So that is why this ITU becomes very important for us. However, recently we have got permission to use L1 also. So in the latest IRNSS satellite we have L1, L5 and S band. All the three carrier waves has been used in the IRNSS. We will get into details during a dedicated lecture on IRNSS. And this ITU held a World Radio Communication Conference every 3 year or 4 year. Okay, currently the duration has been made 4 years. So in that particular conference, they announced the latest developments which are there in the pipeline. Okay, so in the United Nations and different forums, there are different type of solutions which are being looked forward for the future applications, like getting direct download of even satellite based datasets into your PDAs, pocket digital assistants. So those things are also already scheduled for 2026 meeting, 2027 meeting, for different forums actually. So that agendas are available online if somebody is interested in looking at that. So that is the way the technology is moving forward, and we will see a time soon wherein today, along with the GPS data, we will be getting some more satellite data sets in our pocket digital assistants, PDAs basically, or the possibly the smartphones also. Now this navigation message is divided into 5 subframes. The first subframe contains the clock coefficients. Second and third subframes contain all necessary parameters for the computation of the satellite coordinates, that is the ephemeris data. Please remember, ephemeris data is the like the Cartesian coordinate system we use x, y, z. So similarly, ephemeris data consists of the coordinates of the satellites in their respective orbits in a geodetic coordinate system or a celestial coordinate system. So that way these coordinates are used. Block 3 consist of the fourth and the fifth subframes and contain the almanac data. Almanac data, as I told, it is the chart of all the GPS satellites. They are the artificial satellites. Almanac in Hindi is called the nakshatra, okay, or in Sanskrit also. So almanac is nothing but the nakshatra. So in usual usage of nakshatra, we mean to refer the natural satellites. However, in case of GPS, almanac refers to the GPS satellites. So the term is same in astronomy and in GPS, that is the almanac, referring to the chart of the satellites. Now each of the subframe takes about 6 seconds for the broadcasting or the download to the receiver, and that is why the 5 subframes, that is 5 multiplied by 6, takes about 30-second time for the receiver to receive the almanac data. Okay, so if we have 25 satellites or 30 satellites, we will get 12.5 minutes or 15 minutes of data. So that is the time we should minimum use for any DGPS solution. So this is again referring to the almanac data. Currently all the details are available on the website. If you will just put in the Google or you go to the official websites of GPS, GLONASS, BIDO, Galileo, all the agencies are providing these data sets in real time on the website. They will also provide along with this data on what date particular satellite is completing its life, or if some particular satellite is there as a spare, when it is going to be included in the services. So all that data sets are available in similar tables which are available. Now as we discussed that the code solutions are there and we have a problem with the timing, because on the satellite we have atomic clock and on the receiver we have the quartz based clock. So what is happening that similar signal is emanating from the satellite as well as the receiver. They are same, and this signal is used for computing the synchronization error between the two clocks. So what is being done, because the two messages like 0101, that code is there, so that is made constant for one of the two, either the satellite or the receiver, and the second it slided below that, okay, and it's slided up to the extent that the two become same. So the slide required is actually providing us a value for the clock bias, that how much difference is coming between the two clocks because of the different accuracy and precision of the atomic clock and the quartz clock. Atomic clock on the satellite and the quartz clock on the receiver. We refer the satellites by either the satellite vehicle number or the pseudo range number code. PRN code is given to each satellite. Now this PRN code is uniquely identifying each satellite. It provides timing coordination for the GPS. It enables amplification of the signals. Each satellite sends a unique signal which repeats itself approximately 1 millisecond, and this is helping us in solving the synchronization issue between the atomic clock and the quartz clock on the receiver. Receiver compares cell-generated signal with the receiver received signal for synchronization as shown here in the figure below. Okay, so like that the delta T component is computed for the computation of the clock bias. So in the usual discourse, the computation is for the distance is C delta T, okay, for the entire distance from the satellite to the receiver. However, there is a dt component also which need to be corrected for the clock bias purpose, for the correction of the clock bias. Now here we can have as we have discussed earlier, either we can have the code solution. Using the codes we can derive the solution for the receiver location, or using the code also it is possible. So in code also what happens, this n lambda is there. So when the signal starts from the receiver to the from the satellite to the receiver, we will count the number of complete wavelengths. So the lambda refers to one wavelength and n refers to the total number of complete wavelengths between the satellite and the receiver. So n is referred as the ambiguity. So n lambda will provide us the distance traveled by the wave from satellite to the receiver. Now this is the integer number. Now the distance need not to be an integer number. That means the last wavelength, when it strikes the antenna phase center in the receiver, it will have certain phase which can become translated into the C delta T. Okay. So how we can do that? So we can use 2 pi refer is equivalent to lambda. So unit radian will be lambda by 2 pi, and if your difference of phase as phi for the last one, then lambda by 2 pi into phi, that will be equal to the C delta T actually in terms of length. So there is a computation which we require between the phase difference and the distance traveled. So this equation is very important in gateways. So this C delta T is the last wavelength. Okay, and how much this distance will be? Suppose it is for the L1 wavelength. Then 0 to 2 pi, if it is a complete wavelength, so L1 wavelength is 19 centimeter. We just discussed in the previous slide. Okay, L5 wavelength is 25.5 centimeter. L2 is 23 centimeter. So this C delta T will be less than 19 centimeter, because 19 centimeter it's a complete 2 pi phase. So if it is less than 2 pi, then that this C delta T will be less than 19 centimeter, and this computation can be done with the accuracy of 1%. So this accuracy for C dt as visible in the equation here will be accurate to 1.9 millimeter for L1, 2.3 millimeter for L2, and 2.5 millimeter for L5. So that is the type of accuracy which we are talking about in the phase solutions. And this accuracy is basically in the measurement of the pseudo range, that is the distance between the satellite and the receiver. See, this thing is to be understood. One is the computation of the distance between the satellite and the receiver. So there is a accuracy component for that. Thereafter we are computing the coordinates of the receiver using the trilateration. So then there is another accuracy for the coordinates. So these are two different things. One is the accuracy for the measurement of the pseudo range, another is the accuracy of the coordinate of the receiver. So now when we are performing all this for the computation of the coordinates, we definitely need some kind of parameter like root mean square error we use in mathematics for computation of errors. So similar computation need to be done here also. So a very simplified method has been developed using the satellite geometry for the computation of the parameter called positional dilution of precision, that is PDOP. So we call it DOP in general. So there are 4 types of DOPs which refer to the quality of the signal. Geometrical dilution of precision, if we are computing the accuracies in terms of latitude, longitude, height and time as well. If we are computing in terms of latitude, longitude and time, it is called positional dilution of precision. If we are computing in terms of latitude and longitude only, it is horizontal DOP. If it is only for vertical, it is VDOP. Okay, so it is equivalent to RMSE in Z for height, equal to RMSE in XY for HDOP, equivalent to RMSE in XYZ, or RMSE in XYZ in time. Okay, those who are used to computation of the RMSEs, but let us understand that this is a simpler way. In RMSE, what we are having, if we are computing weight of all people and taking an average, we will deal with a unit for kilogram. Okay, if we are measuring height of all persons in the class and taking a mean median for that, we will have a unit in millimeter or centimeter or foot. Okay, but in this case of GPS we are using a unitless number, that is the dilution of precision. So when we compare the GDOP, PDOP, it is unitless. So, and it refers to the quality of signal, as I already told. So it has been simplified that if after computation we get a DOP which get displayed on the monitor of the GPS, it is between 1 and 3, it is very good. If it is between 4 and 5, it is good. If it is up to 6, we are still using it and calling it fairly good. But if it is going beyond 6, we try not to do the survey at that time. Or if we are performing the survey, during the processing time we can remove some of the observations where the DOP values are more than 6. Okay, so there is a thumb rule which I will explain you with my hands actually. So if you open up your hands like this and you consider the GPS at the bottom of your palm, and these fingertips you consider as the satellites, the general thumb rule is if you spread it like this, okay, the higher the volume, more is the accuracy, lesser the volume, less is the accuracy. Okay, so if you have 10 satellites which are spread like this around the GPS receiver, you will get higher accuracy. However, if the same 10 satellites are there skewed towards one side, we will get the less accuracy. Okay, so we will try to understand that geometrically also in the coming slide. So this is a representation of good GDOP and this is a representation of the poor dilution of precision. Okay, now this is the further geometrical description. What happens when the satellites are spread apart and we create the spheres around those satellite positions using the pseudo range, the intersection results in a smaller uncertainty. But if the satellites are nearby and we create those spheres because of the radius of curvature, what will happen? We will have larger uncertainty. Okay, so this is a geometrical description of that, and that is how we define these good and poor positions of the satellite constellation at certain point of time, because this is a dynamic system. All the satellites are moving in their orbits. Earth is also moving, revolving as well as rotating. So the DOP value also continuously keep on changing, providing us a different solution at every moment. Even if we are standing at the same place, we are going to have a real-time solution for them. Okay, so now we will take some 1-2 case studies before taking up the questions ahead. So now one of the use of the GPS is in the photogrammetry, as you may be aware. So we have the photographs acquired in stereo through the aerial platform like the aircrafts, helicopters, or using the UAVs, or we get the stereo data sets like Cartosat, Allos Prism, Pleiades 1A, 1B, Pleiades Neo data. Okay, so I'm just taking name because possibly you might have encountered them during the remote sensing lectures. So we have different satellites or aerial platforms which provide us stereo data. And now these platforms also have GPS on board them, providing us the location XYZ, and they have the attitude parameters, that is omega, phi, kappa, rotation about XYZ axis also from the inertial navigation systems or the IMU, inertial measurement unit. So GPS plus IMU, they provide us the coordinates for the exposure station, and on the ground we do the GPS survey so that we can carry out the satellite triangulation or the arrow triangulation if we are using aerial data, or satellite triangulation if we are using the satellite stereo data pairs. Okay, so this solution should be better than 1 pixel. Okay, and we may need to do photo processing if we are using magazine camera. If we are using the digital cameras, then we need not to do the photo processing. So making it short for with respect to the GNSS, so we have an important role here for the GPS in the area of satellite triangulation, because the accuracies of the different products like the digital elevation model, contour generation, or the map generation using the ortho images, or the 3D maps, which can further be taken into the GIS and engineering softwares for implementation of the some of the engineering works like the layout of water pipelines, sewage pipelines, or construction of road. So here the accuracy of all those will depend upon various factors at each step. So out of them, GPS is one of them. So we have to do a strict quality check in all these procedures so that the final accuracies achieved are within the requirements of our project. So that has to be seen. Accordingly, methods has to be selected. So these photographs show the measurement of GPS coordinates at the end of bridge. This is for a base station on a terrace. We can generate the DEMs or the either grid format or the tin format. We can create 3D maps in digital environment by digitization in the 3D environment using stereo glasses. We can generate the contours, we can create the maps, and we can overlay the vector layers over the ortho images also. So earlier we were using it in an analog form or the analytical photogrammetry. These systems, somewhere you might have seen in the photogrammetric workflows. So these are the digital systems which we are using nowadays. This is the analytical system where partly we have manual operations and partly we have computer based operations. This is fully manual operation. So this is analog system, these are analytical systems, and this is a digital system. So like that, in all these systems we use the GCPs. So this is one of the aerial photographs for the Switzerland. This data set used to come as a sample data along with the procurement of these analog receivers. So these what we see here, these are the control points on the photograph, control points and the tie points which are placed on the photograph. So like that we perform the triangulation using different blocks. We are not getting into the details of this. However, we have to understand that we have to use the GPS for the triangulation or the georeferencing of the mono or stereo data sets, and we have to use the von Gruber locations for that so that we can remove the Y parallax. That way we have to do the planning for the GPS properly. We will look at this aspect in the coming lectures also. So today we will stop here and we will take up questions from you.